Okay, is this thing on? Okay, welcome to today's talk by Sean Colin-Ellerin, who's going to tell us about bootstrapping quantum extremal surfaces.
Thank you, Simon. Okay, well, thank you for the invitation to speak. I'm very happy to be in Florence. So I'm going to talk about some I've been working now. So it's based on a paper with Alex Berlin last summer, as well as some current work in progress with Alex and Onkar, some work in progress on myself. Okay, so the basic idea is the following. So I think we can all agree that one of the central players in the connection of information and quantum gravity has been this quantum Hrt formula. So the proposal due to Netta Engelhardt and Aaron Wall is the following. If I want to compute the entanglement entropy in the CFT for some region A in some state psi, the corresponding quantity in the bulk that I should compute is the extremization of the generalized entropy. Okay, so the gamma entropy of the homology surface, gamma region A. So here's the picture. If I have a slice of ADS3, here's my surface gamma. Well, this is the region bounded by gamma and A. So the general prescription is, as proposed by those authors, is that you should compute each side order by order in 1 over n, and it should agree order by order in 1 over n. So at leading order, you just have the area term, that's the Hrt formula. Then at first subleading order, you don't have to re-extremize, you just have the area of the classical extremal surface plus entanglement of bulk fields in this region sigma, that's the Faulkner-Lefkowitz-Maldacena formula. But then at subleading order in 1 over n, it becomes non-trivial. And the proposal is that now you need to extremize this sum. So this sum is the generalized entropy. Okay. Now, this formula has been beautifully applied to compute the page curve. But in that calculation, it seemed like you only needed semi-classical gravity. The CFT has access to a lot more than just semi-classical gravity. It has access to all of the strings and branes and so forth. But it seems like you only need access to semi-classical gravity. So the question I'm going to ask today is what exactly in the CFT do you need access in order to compute the right-hand side? So what quantities in the CFT, in particular, what OPE data in the CFT do you need to actually compute this quantity on the right-hand side? So that'll be the goal of the talk today. And the other goal is just to really unpack this formula. So we want to understand how do terms on the left-hand side correspond to terms on the right-hand side. And so one of the goals will be to actually construct a dictionary between these two sides and actually check this formula. So to our knowledge, this formula has not actually been checked explicitly where someone's computed both sides and checked that they actually match. At the non-trivial order where you have to actually externalize the full generalized entropy. Raphael?
Yeah, just so I understand the motivation. So the thing that's not surprising, right, is that this formula works independently of the CFT. Since it's derived from a gravity path integral, it will work even in asymptotically flat space when there is no CFT dual.
Right.
But what you're saying is you want to sort of identify individual elements of this formula in the CFT? Is that a fair?
Yeah, that's right. So you could have taken this right-hand side and say this is the correct formula for entropy and gravity. Forget about the CFT, I agree. But if you want to say that it's equal to some CFT entanglement entropy, then you should really be able to match the two.
Thank you, yeah.
Yeah. Okay, so, yeah, question? Yes. propagating graviton? Is that what you said? Yeah, that's right. That's right. So today I'm going to talk about ADS3CFT2, and there we won't have to worry about gravitons, as I'll explain. But at the end, I'll talk about some work in progress by myself where I'm trying to understand exactly this question of propagating gravitons and how to check this formula. Yeah. So that'll be the last part of the talk. Okay, so just to state the goals a little more clearly. One, we want to construct a dictionary between CFT OPE data and contributions to the generalized entropy. And the second goal is just to explicitly check Engelhardt and Wall's proposal. In a simple example where we can do everything explicitly and analytically and so forth. Okay, so let me just tell you what the dictionary is. It won't really make a whole lot of sense until I actually tell you the calculation, but I just want to give you sort of the general idea of where we're headed so you see what the basic dictionary is going to look like. So here we have the CFT entanglement entropy in some state psi. And this will just be some perturbative state. I'm going to be thinking of perturbations of the vacuum ADS. I won't be doing black holes or anything high energy. And here we have the extremization of S-gen. Okay, so as I said, I'll be working in ADS3CFT2. So the parameter is really the central charge C. And at this order, this is the FLM order. There's two contributions to the OPE. One is the identity block, and one is the contribution of double trace operators. Okay? And these correspond in the bulk to the area of the classical extremal surface with the back reactive metric. That's what I'm calling G1. That corresponds to the identity block, and these double trace operators correspond to the bulk entanglement entropy. Okay, so notice here that there's no gamma 1 G0 term because of classical extremality. There's no first order variation in the surface. So this is the only correction to the area at this order. And then there's a bulk entanglement piece. Okay, now the interesting order is 1 over C. That's where quantum extremality becomes important. And here, there's various contributions. So this operator O actually picks up an anomaly, and I'll explain later how we compute that. So there's a correction to the dimension of this operator O, and the identity block gets a corresponding correction, plus there's just the stress tensor contribution. This is just the global block in 2D, okay? There's anomalous dimensions of these double trace operators, and then there's corrections to their OPE coefficients. Okay, and this corresponds in the bulk to corrections to the area term. And these terms, this is work in progress. So I can say at the end, we understand about this part of the dictionary, but we're still trying to understand it. And this is the work in progress with Alex and Onkar. We think that this is going to correspond to the bulk entanglement entropy, but we haven't fully part out.
Sorry, can I ask a question? So normally you would think that 1 over n contributions in the symmetric orbifolds, which is the dual CFT, should come from covering surfaces at a higher genus, and should therefore come from a higher genus term from a sort of string worldsheet perspective. Mm-hmm. So in which sense do these terms come from higher genus? I mean, how does your keeping track of the OPE dependence correspond to the sort of higher genus covering way of organizing the 1 over n expansion in the symmetric orbifold?
Yeah, so here we're imagining that you have some large n theory with some large delta gap, so all of the single trace operators are highly suppressed by this order delta gap, and so the only single trace operators of this order are just the stress tensor. So I think it's very far from the symmetric orbifold point. It's like the supergravity point in moduli space where everything is lifted except for the stress tensor.
I see. But if you were to do this at a symmetric orbifold point, could you translate this, or is this very unobvious how that would translate?
I think it's unobvious how the dictionary would work at that point in moduli space. Yeah, it's a very interesting question, but we haven't tried.
I mean, the other thing that's surprising is that at that stage, there's really stringy correction contribute from the worldsheet perspective. Yet, as you were pointing out, you have still a classical geometry formula. Do you have a sense in which, I mean, is this some sort of effective description keeping track of the stringy corrections, or how should you think about this?
Yeah, I don't know how the stringy corrections are packaged into this formula. It's a great question. I'll have some comments at the end, but I don't know how to actually get... I agree that it's still semi-classical, but I don't know how to understand the stringy corrections to this formula. I can briefly say that I know that Lorenz Eberhardt and Felix Hell and Shota Komatsu have some work in progress on understanding this. Trying to understand this formula for the k equals 1 string theory in ADS3. But, okay, we haven't thought about it.
But we're doing like intervals in the vacuum of ADS3, or?
Yeah, that's right. It'll be a single interval here, yeah.
Oh, a single interval?
A single interval in ADS3 in an excited state.
Oh, I see, okay.
In an excited state, yeah. So let me tell you the general setup. Okay. Actually, before I get started, let me briefly comment that you might have thought that this thing is just impossible because you would have said that both of these contributions are divergent, and the general law is that only the sum is a finite quantity, and that divergences in the entanglement entropy in the bulk renormalize G Newton, and you really need to think of this full quantity. That's the only thing that physically makes sense. The way that I'll do the calculation is I'll actually consider the vacuum subtracted entanglement entropy, and that thing will turn out to be finite, and there you can actually attribute finite terms between the CFT and the bulk, as we'll see. Okay, so let's get started. Okay, we're just going to consider some excited state in the CFT O, which is given by a primary operator O acting at the origin in the plane on the vacuum. So this operator is some light operator whose dimension does not scale with C. And the interval that I'll consider is just some angular interval on the cylinder. Okay? And the reduced density matrix is just the standard reduced density matrix. I'm going to use psi and O interchangeably because psi will be the bulk to O. So hopefully that's not confusing. And we're just going to use the replica trick to compute this. So we want to compute the vacuum subtracted entanglement entropy in the state psi. And we compute this by just computing the Renyi entropy. Okay. And the key point is that to compute this Renyi entropy, we're going to compute a 2 endpoint function in the CFT. So is you take the cylinder, so the setup is like this. Our operators are inserted at the top and the bottom of the cylinder. And you take n copies of the cylinder glued across A. You map that to n copies of the plane glued across A. Then you uniformize the plane. And what you get is 2n operators distributed in the plane on the unit circle. They're distributed like this. So here is n equals 4. Here are my operators O, O. And this distance here is theta over n, where theta is the size of the interval. Okay, so that's what you get from this uniformization map. And the corresponding vacuum subtracted Renyi entropy is just given by a 2 endpoint function. Okay. So notice that there are no twist operators here. I just had a 2 endpoint function on n copies of the cylinder, and then I map that to n copies of the plane, and I uniformize. The reason I have no twist operators is usually we don't do this uniformization map because there's an infinite divergence coming from the conformal factor when you go from n copies of the plane down to the single copy of the plane. But here I'm doing vacuum subtraction, so that infinite divergence cancels out, and you just get this 2 endpoint function. There are no twist operators in the game here. Okay, so now the goal is to compute this 2 endpoint function, but in the small theta limit, these operators O become close, and you're just computing an OPE of these operators, pairwise. So you have 2n operators, and there's n pairs of operators, and you're computing an OPE for each of those pairs. And so you can compute this thing, and this is where the bootstrap of the title of the talk comes into play, because you can actually compute this 2 endpoint function order by order in 1 over c using large C bootstrap. Okay, so you just get generalized free fields. And so it's just Wick contractions. And there are 2 contributions in the small theta limit. So you get the identity contribution, and you get double trace operators. So there's really all double trace operators appearing in the OPE, but at leading order in small theta, you just get the 0, 0 double trace operators. Yeah?
So given that you're taking the small theta limit, do you have a sense of how the higher order corrections in theta play against the higher order corrections in 1 over c?
Well, I think it's an order of limits. Like you take C large first, and then you take theta small. So I think it's fine. I think there's no like competing between small theta and large C.
But if I were to say, try to look at next order corrections in theta,
Yeah.
then I would have, at order C naught, I would have some tower of corrections in theta, and then at order C1 or C minus 1, I would also have a tower of corrections in theta.
That's right.
Okay, and you're just computing the first one in each C sector?
In each C sector.
Okay, thanks.
That's right.
All right. Yeah, I'm sure you said this, but so the operator acts at, I'm having trouble with the notation a little bit. The operator acts at 0, is that right?
Sorry, it acts at 0 on the plane, which is really minus infinity on the cylinder. So here I wrote it as 0 on the plane, but yeah, it's really here on the cylinder down.
I see. You just prepare the state, yeah.
Yeah, exactly.
The usual
You're just
way.
preparing the state.
Okay. And O is just any, so the only thing we're restricting is the dimension, is order 1.
Yeah, that's right. We're assuming O is single trace, yeah, exactly.
And O is single trace.
Exactly. So it's some single trace light operator in the CFT, and we're assuming that we're in a holographic limit where we're dual to semi-classical gravity, so all single trace operators other than the stress tensor are lifted by delta gap. So they're all suppressed by 1 over delta gap. Yeah.
Given that we're not talking about some particular gauge theory, but just some general conformal bootstrap arguments,
Yeah.
what do you mean by single trace?
Well, yeah, what you really mean by single trace is that there's some scaling of the OPE coefficients. So the general statement is that OPE coefficients of O, O, and double trace are order 1, but OPE coefficients of O, O, and some other single trace, let's call it O prime, is order 1 over root C. So there's some hierarchy of OPE coefficients like this.
Okay.
Where with its own double trace operators, it has order 1 OP coefficient, but with all other single trace operators, it's suppressed.
Okay, and so you can consistently classify operators into some trace order just by looking at the coefficients?
That's right.
Okay.
That's right. Okay. Good. So now the interesting order is order 1 over C. This is where you have to use the large C bootstrap. And there's a very beautiful paper by Gobay, Collier, Maxfield, and Perlmutter where they actually computed these 1 over C corrections to OPE data. So at order 1 over C, good. So there's corrections to the dimension of these operators, O, which I'll explain. And then there's the stress tensor exchange in the O. Okay, and then there's the anomalous dimension. And these are corrections to OPE coefficients. And what's remarkable is that you can just invert the stress tensor block in the T channel in order to figure out what the corrections to these two quantities is at order 1 over C. So I'll write them down, but they're very simple. Okay, so these can be computed, and so now you get different contributions to the entanglement entropy, and you can just write them down. Okay, there are some complicated functions here which I'm not going to write explicitly. I just want you to see the theta dependence of these functions. They're in the paper if you want to see the exact form for these H-dependent coefficients. Okay, so you can compute these explicitly in the CFT, and so now you have an explicit answer for the left-hand side of the formula, which I erased, but for the quantum Hrt formula, you have an explicit answer in the CFT, and so now you can go, can we actually compute this in the bulk by extremizing the generalized entropy and get a match? And the basic way that you will be able to match terms between the two sides is that you notice that these have different analytic structure in theta. So these terms are analytic in theta, but these terms have monodromies in theta, right? For generic H, these will be non-analytic in theta. They'll have monodromies around theta equals 0. So you can match the different terms on the two sides just by looking at the analytic structure in theta. Okay. Good. So now let's talk about the bulk.
So in the CFT, we're not working at small theta.
We technically are. I mean, by taking this OPE limit, we're working at small theta, so you should really expand each of these functions at small theta because technically speaking, there's an OPE limit.
In other words, there's other corrections at some order in theta that haven't been calculated here?
That's right.
So what order in theta are these valid to?
These are valid at first order in theta, so this will be theta to the fourth, and it's valid at that order. But then at subleading orders, there'll be corrections. Yeah, I wrote it this way because we got exact answers in theta for this OPE case, but really you should think of this as a small theta expansion of these functions.
I see.
Yeah.
Right.
Yeah.
So, and it's not totally clear, like, that this is a consistent expansion in the sense that you might be throwing away things at that order, corrections to like delta S3 that are at the order of the delta S2 corrections you're keeping, or something like that?
Yeah, so that's right. So you might have thought that this is subleading with respect to this, but the point is that they have different analytic structure in theta. So you keep terms based on their analytic structure in theta, so you have terms, okay, I didn't write down these terms, but you also get terms that are like theta to the 4h. And the point is that they have different analytic structure, so you keep each type of analytic structure in theta, and you expand each of those separately.
Okay.
Yeah.
Yeah, sorry, I have a question in this regard. So the fact that you are working at small theta, it should fix the sheet on which you are evaluating the blocks, right? So, I mean, you want to recover the small theta singularity, right? So that means that you should take these two operators on the same block. So that doesn't leave any monodromy at that point, right? I mean, it shouldn't.
I think if you had the exact answer, you would have no monodromy. But because you're looking at each individual block and you're expanding, you do get a monodromy, right?
Right, but implicitly, I mean, working at small theta, you're assuming that these two operators are, I mean, so you're fixing the sheet on which you're evaluating the block, right?
I'm not sure. What do you mean by fixing the sheet? I mean, you uniformize down to the plane. The original.
Okay, I guess we can discuss it later. It's,
okay.
It's maybe a bit long. Yeah, thanks.
I agree that the full two endpoint function has no monodromies, but the blocks have monodromies, right? So when you look at each individual block,
but
you get
you're approximating a correlator which is single-valued with an object which is multi-valued. So you should specify on which sheet you are evaluating these blocks. And the fact that you're working in a fixed theta, in a small theta expansion that fixes the sheet on which you evaluate these blocks. So that shouldn't leave any monodromy anymore. Because otherwise, I mean, there is something wrong, right? Otherwise, if you are approximating something which is single-valued with a multi-valued object, then you have to specify how to get rid of this multi-valuedness. And that's fixed by the fact that you're working at small theta, I think. But okay, I guess we can discuss it later. Yeah.
Let's discuss this more offline. I'm not sure immediately what the answer is to that. Yeah.
I'm getting a little worried about Matt's question. So I understand how 3 and 4 have like funky monodromies around theta equals 0, and you can identify those using that structure. But suppose I'm trying to figure out what the contribution is to 1 versus what the contribution is to 2. So at small theta, S1, delta S1, is some order 1 number. It has a smooth limit as you go to, or it has a finite limit as you go to theta equals 0.
I think this is order theta squared. This is order theta.
Okay,
fourth?
okay. So all right. So let's say that 1 is order theta squared and 2 is order theta to the 4th.
Yeah.
Now the thing I'm worried about is that because I'm only taking the lowest order in theta in each, how do I know that if I were to keep computing to higher orders in theta at 1, I wouldn't get a theta to the 4th term that would complicate my ability to match delta S2?
No, you do. You do get order theta to the 4th terms here that you have to consider both. So there are subleading terms that are like, okay, I didn't write them, but this is the term coming from the stress tensor, right? The next subleading term that you really need to worry about is terms that are like 2 stress tensors. It's like TT operators. And those ones we're definitely suppressing, but these 2 expansions are valid up to that order, so like theta to the 8.
Okay. So both of these are valid up to theta, including theta to the 4th, and I don't need to
That's right. In
worry
fact,
about
including
missing.
theta to the 6th, but you're suppressing theta to the 8 because then it starts to mix with TT operators
Super.
that are exchanged in the S channel.
Okay, thanks a lot, Sean.
I understand this is a little confusing, but hopefully that clears it up. Okay. Good. So,
Yeah, there's just, okay. This is delta H?
yeah, so I'll explain what this is. This is actually an anomalous dimension of the single trace because they're not protected in this approach. And I'll explain how
Okay.
I'll explain it
And
later.
I guess that's also going to make it clear how you have a theta sitting in the first term.
Sorry, there's a...
There's a theta out front of the code. Yeah. This.
This is order squared.
No, I understand, but okay. So you're going to tell us where delta H comes from, and probably that's going to explain why you have this peculiar structure in the first slide then too. Okay.
That's right.
Okay. Thank you.
Okay. Okay, good. So now let's talk about the generalized entropy, which is the interesting part of the story, because I think it's the most confusing part. And I think there are a lot of subtleties in how you actually compute this, and that's sort of the whole point of this program. Okay, so this operator O in the CFT corresponds to operator psi in the bulk, where I just canonically quantize a scalar field in the bulk, and I look at A00 dagger acting on the vacuum. And then I can think of expanding the metric order by order in G Newton. Actually, I want to keep the next term. And similarly for the surface, okay. So we want to compute the generalized entropy. So at order G Newton to the 0, you just have the expectation value of the area operator the bulk entanglement entropy. Okay, so this G1 comes from taking this scalar field that I've canonically quantized, computing the expectation value of the stress tensor, back reacting on the metric. That gives me this G1. And then I compute the area of the classical extremal surface with that new metric. And that gives me some contribution to the area term at order G Newton to the 0, and then I compute the bulk entanglement term. So this bulk entanglement entropy term, the way you actually compute this piece at this order is you can go to Rindler coordinates adapted to the entanglement wedge, and then you can think of this A00 dagger as a small perturbation of the thermal state in Rindler, and then you can just directly compute the trays. So you can just directly compute using Rindler techniques. So that's the way it goes. And okay, I won't write down what you get, but it exactly matches this contribution in CFT. So you get an exact match, and you get this contribution that I wrote down at the beginning, which is that this area term exactly reproduces the identity contribution, and this bulk entanglement entropy term exactly reproduces this contribution from the double traces. Now there's a cancellation that happens. So this thing gives you something that's order theta squared plus something that's order theta to the 4h. And this thing gives you something that's order theta to the 4h plus something that's order to the theta to the 8h. These theta to the 4h terms actually cancel between these two. And there's a nice explanation for this, which is it's implied by the first law of bulk entanglement entropy. So you can relate this first order correction to the bulk entanglement entropy to the expectation value of the modular Hamiltonian, first law of entanglement entropy in the bulk, and then you can use, it's essentially Hrt formalism to relate that to the, to argue that it has to cancel against the area term in order to reproduce the expectation value of the modular Hamiltonian in the CFT. So there's a very nice explanation for why these two pieces cancel, and you're left with theta to the 8h and theta squared, and that's how you can match it to the CFT. Yeah, John?
So I'd like to understand the notation of this SGen formula that you've written here. So we defined psi in the bulk as basically like a bulk field theory state that you get by acting with some particular creation operator on the vacuum. I'm a little confused as to what psi 0 is. If I think about, okay, like quantum mechanical perturbation theory, then, we can talk about orders of energy eigenvectors because, what vector is an energy eigenvector changes with the order of your perturbation. But here, the definition of psi seems kind of unambiguous. It's just a particular operator acting on the vacuum state. So I'm a little confused as to how the state itself has a perturbative expansion.
So this psi 0 is, I've canonically quantized on vacuum ADS, and I've acted with a dagger. Now, when we actually go to the next subleading order to compute quantum extremality, we're going to have to quantize our scalar field on the back-reacted geometry.
I see.
And that will give us a new state, which is a correction to this psi naught state.
I see. Okay.
Yeah.
Great. Thank you.
It's the fact that you have to order by order.
I see.
And you have to compute it in a new state now in order to properly back-react.
Good. So if that's the case, I think I'm a little, maybe this is just notational. I'm a little confused as to why the area operator that appears in this expression is then the area operator with the perturbed metric, because I thought that psi naught was supposed to have a completely unperturbed metric.
So you're computing by order in G Newton. So you could really think of there as being a full psi that's an expansion. It's like psi naught plus psi 1 plus ... And at leading order in G Newton, it's just the expectation value of this.
So why is it G1 instead of G0 is, I guess, my question.
Because that's the first subleading order in G Newton. Right? The area term is A for G. So this term is like G.
Yeah.
And that cancels against the 1 over G Newton in the area term?
Yeah, okay. I think it's purely a notational concern, so I can let you keep going.
Sounds good. Yeah.
But, I mean, maybe the confusion is, I mean, you're looking at the first change in the metric because of the back reaction. So that should actually be independent of psi naught in the sense that this expectation value actually, it seems like, you're really just calculating an area in a perturbed metric and not a matrix element. Is that correct?
That's right. Yeah, you could technically just drop the psi naughts and just say I'm computing the area in this back reactive metric.
Yeah.
I think people like to talk about the area operator, so then you want to think about it as an operator, but you just said it's some area of some metric. Forget about operators.
Right, I mean, that operator is the identity on a huge subspace that psi naught happens to be sitting in.
That's right.
Is that right? I mean, it's, yeah, it doesn't actually depend very much on psi naught.
That's right,
Okay.
yeah. Good. Okay. So that's still not the interesting case. That's just the FLM order. So now we want to consider quantum extremality. And this is where things get much more interesting. Okay. So let me just write out all of the terms that contribute. Okay. Okay. So first, you backreact a second time on the metric. That's this G2. And you compute the area of the classical extremal surface for that second order backreacted metric. Then you have the bulk entanglement entropy, but metric variations of the bulk entanglement entropy in the classical entanglement wedge. This term is a little more tricky. So this term comes from the fact that at subleading order in G Newton, you no longer just have a Fock space. So there I just had a dagger acting on the vacuum, but at subleading order you have to break the Fock space because now you have interactions with gravity. And in particular, two particle states get a non-trivial binding energy due to gravitational interactions. So there is a breaking of the Fock space, and that's what this term corresponds to. And then we have the actual extremization. This is the quantum extremality piece. And so here you have the area of gamma A1, and let me say that this is really gamma A1 squared. Classical extremality says that there is no gamma A1, but there can be a gamma A1 squared. Okay, you have the area in the backreacted metric of the new surface, this quantum extremal surface, gamma A1, and then you have the shape variation of the entanglement entropy, which is giving you this entanglement entropy in the new entanglement wedge, once you've now computed the quantum entanglement wedge. So you have to compute all these contributions, and it turns out that the bulk entanglement entropy terms are very hard to compute. So I can say something about them at the end. That's this work in progress with Alex and Onkar. But for now, I'll just focus on all of these area terms that appear here. And I'll explain how this works. So maybe I won't actually write down the explicit expressions for time.
Just to stop you for a second, is there a finite renormalization of G Newton as well?
We don't see any renormalization of G Newton because we just compute delta S. And everything seems to be finite. So we don't seem to be seeing any kind of renormalization of G Newton.
So G Newton is just fixed number from in these computations.
That's right. Like the vacuum is subtracting off all the divergences that we seem to be getting in this calculation. And so we don't seem to need to actually consider the renormalization of G Newton.
Sorry, but isn't the relation between G Newton and C actually a power series? Isn't that relevant? Because on one side you presumably have C's, you're expanding in C.
Yeah.
On the other side in G Newton.
You mean like there are corrections to the Brown-Hrt formula for
Yeah.
the relationship between C and G Newton? Yeah, that's a good question. Yeah, so we didn't consider these corrections to the Brown-Hrt formula.
Why are there corrections? I thought this was just true at any C.
Yeah, it's a good question. I don't have an answer off the top of my head.
I mean, those are the ones, if you just consider a single interval in the vacuum, on one side you have an exact formula in terms of C. On the other side, in principle, you should use FLM, and there would be all these extra contributions from the entanglement of the bulk fields that would depend on your field content. And so that's one way to see from an entanglement entropy calculation why there's this, why they're not just, why it's not exact, why the Brown-Hrt formula is not exact. So naively, I would think that would be relevant to you, but it may be the fact that you're doing the vacuum subtraction is what's kind of deleting all of those corrections, because maybe the corrections are the same in the vacuum as in your excited state, and so you just don't see them.
Yeah.
That seems possible.
That's possible, because already in this order you get an exact match. And you might have already thought that there were corrections at that order, right?
Yeah, I suspect it's because of your vacuum subtraction.
Yeah. Yeah. Question?
Yeah, I had a, yeah, the question was about the vacuum subtraction. So are all the terms on the right-hand side of SGen like vacuum subtracted quantities? Every term is finite as well?
Every term seems to be finite. So I can't say definitively about these bulk entanglement terms because we haven't finished computing them. We only have some pieces of it.
Yeah, I think that was the one I was worried about because if you change the area of the surface, that's so the order that you have to worry about that you're computing bulk entanglement with a different area, there you would expect, the vacuum subtraction's not going to get rid of a divergence there because the vacuum divergence, scales like the area. So if you change the area, you get a divergence there. But yeah, I was just curious if you see that somewhere.
We don't seem to see any divergence in the bulk entanglement entropy. So at leading order, so when you compute this bulk entanglement entropy, let's say this piece, the shape variation, which I think is the term you're worried about, where now you have a new surface, sigma A1. So that term actually doesn't get any contribution from the vacuum. So you can compute this thing perturbatively, and there's a first term which just comes from the vacuum, and then there's subleading corrections that come from the fact that you're in a non-trivial state. And the leading correction coming from the vacuum just seems to be 0 for this shape variation. In other words, in the vacuum, there's no quantum extremal surface. If you just had the vacuum state, you would just always have the classical extremal surface. And only when you have a non-trivial state do you actually get a new surface that's not the classical extremal surface. And that thing seems to be finite. But yeah, I don't exactly understand why. It's like the leading divergence, the one that comes from the vacuum, is just not there because there's no quantum extremal surface in the vacuum. And then it seems like there are subleading corrections to the entanglement. You're in 3D, right? So the leading correction is 1 over epsilon. That's the divergence, and then there's finite terms. There's a universal term and so forth. And that 1 over epsilon term just seems to not be there for this piece because there's no vacuum entanglement entropy. Sorry, there's no vacuum quantum extremal surface. So it seems like what you only get is the universal term that appears in the entanglement entropy in 3D. That's at least what we found so far, but I can't say for sure because we haven't finished the calculation.
On that point, just a really pedestrian comment is that it's generally true in any system that shape variations of the entanglement entropy are finite, even though you're moving the surface and changing its area. Like if you have, you know, a 2D CFT and an interval in the vacuum, the entanglement entropy is log length over epsilon, and when you take derivatives of the length, the epsilon just doesn't contribute to that at all, and you end up getting rid of the cutoff. This is just sort of a general fact that it seems to be that in 2D, yeah, certainly.
Yeah, we're in 3D here.
But I think this is generally,
But-
you know, the shape variations are generally at least supposed to be finite. But. Oh, really? Okay. Well, never mind. I regret my comment.
Okay, so I want to briefly, so I'm not going to write down the formulas for these area terms. They're in the paper if you want to see them. They're very complicated. Comments first. I want to explain how I compute this delta H. So what you really have to do so this confused us for a long time about how to get this delta H, and what you have to do is take this second order back-reacted metric and compute the ADM energy of that space-time. And when you compute the ADM energy of that space-time, that gives you some correction to these dimension of these operators. So if you compute the ADM energy of G1, you just get 2H. But if you compute the ADM energy of the second order back-reacted metric, you get a correction, and that's what we call delta H. And you need to include this in order to get the correct correspondence between the bulk and the boundary theories. Okay, and your question, Christian, about why you get this funny structure, it's basically just coming from the structure of the identity block in 2D. Like in 2D CFTs, the identity block has this funny structure where you get these two terms. I don't know if I have a better explanation than that, but that's essentially where it comes from. I can show you the exact computation offline.
I guess maybe the question is, why isn't it periodic in theta?
Oh. Yeah, I guess the full expression should be periodic in theta, the full expression for the entanglement entropy, but if you're just looking at a single term, then I don't see why it has to be periodic. Like a single term in the small theta expansion doesn't have to be periodic. Okay, so I'll write down what the ADM energy is. So at leading order, you just get the Casimir energy on the cylinder. And then at subleading order, you get this 2H that I mentioned. And then at subleading order, you get a non-trivial contribution. So this here is what I'm calling delta H. Okay, good. So, oh, yeah.
It's going to be a very pedantic observation, but shouldn't you call the whole thing delta H? Including the 1 over C, so that's to say that the anomalous dimension is order 1 over C?
Yeah, I think I put delta H over C here, but you should really call the whole thing delta H.
Okay.
Okay. So now I want to tell you maybe the most interesting part of the paper, which is why we can actually distinguish between the area and the bulk entanglement term, and why we can actually associate contributions coming from the area to contributions in the CFT, contributions from the bulk entanglement to contributions in the CFT. And it comes from a surprising fact of the quantum extremal surface equation. So now this piece here, this quantum extremal surface piece of the generalized entropy, we're going to go to Windler coordinates. For the entanglement. Okay, so metric takes and these coordinates are particularly, the classical extremal surface is just at rho equals 0. Okay. So that's just the Rindler horizon of these in these coordinates, or rotation surface of the Rindler horizon. So what that means is that this quantum extremal surface is just given by g Newton times some rho of x. Okay. So the goal is x. That's the function that describes the quantum extremal surface. So.
Sean,
Okay.
do we have some a priori reason to know that the quantum extremal surface is going to be deformed in a space-like direction?
We expect it will because everything here is time reflection symmetric. So
Okay.
we expect that everything will just be in a spatial direction.
Oh, okay.
There's
Yeah.
no way for there to be any time variations of the surface. Yeah. Okay. So this shape variation of the entanglement entropy that I wrote over there has a very beautiful formula due to Rosenhaus and Smokin. So you might have thought that it's a complicated function of the full entanglement wedge, but it actually turns out not to be. So it's given in the following way. Okay, so it's an integral over all of Euclidean ADS3. This change in the metric is the diffeomorphism that maps you from the classical extremal surface to your surface rho 1. So this is the corresponding diffeomorphism. This is the bulk stress tensor and the bulk modular Hamiltonian for the excited state psi. And you're supposed to compute this correlation function in the state psi. It's really the connected correlator in this state psi. But the point is that this is a diffeomorphism, so you can actually integrate this whole thing by parts. And it just becomes an integral over the classical extremal surface. So this thing becomes the integral over the classical extremal surface. And this is what makes the whole calculation work, because if you just had this quantity, you wouldn't know how to take variations with respect to rho 1. But because you can do this integration by parts and just write it as an integral over the classical extremal surface weighted by rho 1, now you can actually take variations with respect to rho 1 and get a quantum extremal surface formula. Okay. Good. So that's the bulk term. And of course, the area is also an integral over rho 1, so you can vary everything with respect to rho 1. Yeah, Matt?
What happened to the indices?
Happened to the...
I guess there's a normal vector on the surface.
Oh, sorry. Yeah, thank you. This should be rho. Thank you.
Normal. Okay.
Yeah, exactly. It's the normal to the surface, so it's rho.
One more question on this. Is this just the first law of entanglement? Like that the variation in entanglement entropy is delta rho times the modular Hamiltonian, but adapted to the fact that delta rho is a diffeomorphism and therefore an integral of the stress tensor?
Exactly. So
Okay.
when you do that, when you plug in delta rho here, for metric variations, the delta rho is really delta GT because
Right.
the stress tensor sources metric variations in the path integral,
Yeah.
so it brings down a stress tensor. Exactly. And that's what gives you this. So the derivation is actually, it's not a very complicated derivation at all. Okay, good.
Sean, how
Yeah.
are you doing for time?
Oh, can I just take 5 more minutes?
Yeah, that's fine.
I'll just finish writing down the formula for the quantum extremal surface, and then I'll conclude.
I'll try
okay.
to suppress questions a little bit, let you finish.
Okay. Okay, so when you do this, you get the following formula for the quantum extremal surface. It's a very so this piece here, which I'm calling the potential, the entanglement entropy potential, is just this piece. This V geometric is coming from these variations of the area term here. They're written down explicitly in our paper. But the point is, the key punchline is that this is just a first-order linear differential equation that's inhomogeneous. So the solutions to this equation are just sums of solutions where I only have VE or I only have VGO. That's just a simple fact about differential equations. And so it means that you can write this thing as a sum of terms. So it's like the quantum extremal surface has like two forces pulling on it. It has one that's purely geometric and one that's purely coming from the entanglement entropy, and they don't mix in any way. They're like completely uncoupled forces in some sense that are pulling this quantum extremal surface. And so you can just solve for each of these individually. And what we computed in our paper is this term, because we can compute this thing explicitly. And then you plug it back into this formula, and you compute the corrections to the area term coming from this, and you get an exact match with the contributions. Non-trivial match. Like the functions of H are very complicated, and it's not like it's just a multiple of H or something. It's a non-trivial match between these two sides. Okay. So maybe I'll just write that, and then I'll conclude. So this gamma A GO1 is this rho 1, this rho GO1 piece. Okay, so let me conclude before Simon kicks me off. So to unpack this quantum extremal surface formula and actually construct a dictionary between contributions in the bulk and contributions in the CFT, and we seem to find that it's actually possible to do that, which was very surprising to us. And we're on our way to actually non-trivially quantum extremal surface formula, seeing if the two sides agree, and how you actually compute the generalized entropy in the bulk. And it seems like Bootstrap is actually a powerful technique for computing entanglement entropy in non-trivial states in CFTs, order by order in 1 over n. So we usually think about Bootstrap. At large n, you can actually get exact answers for OPE data using Bootstrap. And it seems like this is a very powerful technique for computing these entanglement entropies. And it's an interesting question of how does that correspond in the bulk? And what do we actually learn about generalized entropy from these non-trivial results that the Bootstrap give us for entanglement entropy? So I think it's interesting to ask in particular, can you get string equality? So people have computed 1 over lambda corrections, say in n equals 4 super Yang mills. If you look at correlation functions of the stress tensor multiplet in n equals 4 super Yang mills, you can compute 1 over lambda corrections using localization. And so you can actually use those results to compute these entanglement entropies. And then you can ask, what does that correspond to in the bulk? So we're going to get some non-trivial calculation for 1 over lambda corrections. They're really 1 over n times 1 over lambda corrections to the bulk to the CFT entanglement entropy. Can we use the Hrt formula is? And so I think that's a very interesting question that we're currently thinking about. The other question is what Christian mentioned, which is that can you really graviton entanglement in the bulk? So to my knowledge, nobody's actually computed graviton entanglement in ADS. And you could just ask, does the FLM formula still hold when you include gravitons, and how do you actually compute graviton entanglement? So you can use this formalism. So now you would compute the entanglement entropy in a stress tensor excited state in the CFT. And that was the work in progress that I was going to talk about, but I ran out of time. So if you're interested in that, we can talk offline. But you can compute this stress tensor to endpoint function by taking this small interval limit in higher dimensions in any CFT with d greater than 2. And you can ask, can you match that answer to some graviton entanglement calculation in ADS? OK, I'll stop there. Thank you.
So Agon and Faulkner computed graviton entanglement in 4D bulk, 3D boundary, in the large separation limit, and verified FLM.
They were actually able to get the graviton entanglement?
I think so.
I don't remember them getting the graviton
Well,
contribution there.
they were doing FLM.
Yeah.
Are you saying they were just doing scalars
I
in
thought
the
they
bulk?
yeah, I thought they just had a scalar field in the bulk, from what I remember.
Okay.
I don't remember them ever having to compute the graviton contribution. I think.
It was just scalars? Okay.
I think it's actually not known how to even quantize the graviton in the entanglement wedge. Like, there's a prescription in an appendix of JLMS where they say how you would do it. They say, like, you fix boundary conditions, then you integrate over all possible boundary conditions. But to my knowledge, no one's actually implemented that procedure that JLMS proposed for how to compute that quantity.
I see. Okay. So a question. So I'm sure you said this, and I just somehow missed it. Where was the extremization in this calculation, in the bulk calculation?
Oh, here we extremized this, these area terms plus this bulk entanglement term. And we did that by going to Rindler coordinates.
Yeah.
And then this bulk entanglement term became very simple. Became a simple function of that shape variation, which is the quantum extremal surface. And then I didn't write down the area terms, but they're also functions of rho 1. And then you vary those, and you get, this is the equations of motion for the quantum extremal surface.
Oh, that's the Euler-Lagrange equation?
That's right. This is the Euler-Lagrange equations for the quantum extremal surface.
Okay.
And so then you just need to solve this equation. And it has this very simple form.
I get linearized Euler-Lagrange equation.
That's right.
Which direction does the extremal surface move?
It seems to be moving out. So at least this piece seems to be moving towards the boundary.
Toward the boundary, I see.
That's right.
Is that a... I wonder if there's a general statement about that it has to move toward the boundary. I mean, for small intervals, of course, yeah.
Yeah, I think it's a very interesting question. If you could actually prove that it always moves towards the boundary. I mean, you need to figure out how the entanglement entropy changes, I think, as you...
Right, that should be, you would think that would be kind of a universal thing.
Yeah.
At least for scalars.
Yeah, I mean, as you decrease the entanglement wedge, wouldn't you expect the entanglement to decrease as well? I'm not sure what the exact intuition is there. It's a good question.
Yeah, I don't think it's obvious.
Yeah.
Okay, do I get one more question, Simon? Or? Okay.
Yeah.
Can you do 2 intervals?
Can you do 2 intervals? Good question. It's a different calculation. I mean, you could just do 2 intervals in the vacuum, right? You already get non-trivial contributions for 2 intervals in the vacuum. So you could use either what Matt did or what Tom Hartman did to try to compute 2 intervals in the vacuum, and there you get some non-trivial OP contributions. I mean, you get contributions from all operators in the CFT. It would be very interesting to ask. I mean, in the bulk, I don't think you'll get any corrections to the quantum extremal surface because you're still in the vacuum. So I think...
I don't think that's true.
You think you'll get corrections?
Yeah, because it's trying to maximize or minimize the mutual information. Actually, yeah, I think maximize the mutual information. And therefore, I think they will be pulled towards each other. The surfaces will be pulled towards each other to increase their mutual information, the bulk mutual information. It's true that the single interval things will not be corrected, but the mutual information will get corrected and will, I think, lead to a sort of an attractive force between the extremal surfaces, I think.
I see. Yeah, so here you would have the modular Hamiltonian associated to 2 regions, and I guess that's some non-trivial thing that will
that's non-local.
Move the surface. I see. Yeah, I agree. I agree. It's an interesting question. It's we haven't thought about it, but I think it's interesting.
Are there any other questions? All right, let's thank Sean again.